Welcome to AI Podcast. Today we're digging into a NeurIPS 2025 paper called Lessons Learned, a multi-agent framework for code LLMs to learn and improve.
Nice. Give me the headline first. If I'm walking between meetings, what's the one-liner?
Short version? A small team of code models shares bite-sized tips with each other, what the authors call lessons, and that simple knowledge-sharing loop helps them match or beat much larger single models on standard coding tasks.
Lessons as in advice, not school homework?
Exactly. Think of them as sticky notes. One agent tries an optimization, gets feedback from a compiler or a timer, and leaves a note like, swap the loop order to improve cache locality, or parallelize the outer loop. Inner loop parallelism adds overhead. Other agents read those notes and update their code. The group keeps learning round by round.
Got it. Who led this?
The first author is Yuanzhe, and a senior author is Jichen. The team spans Rensselaer, MIT, in the MIT IBM Watson AI Lab.
So what problem are they actually solving? We already have some big coding models that are pretty good.
True, but those models don't win everywhere. The authors show that on a code optimization benchmark, different models shine on different categories. One might be great at geometry, another at histograms, and so on. So if you only pick a single model, you're leaving performance on the table. Their question was, how do we exploit those complementary strengths without knowing upfront who's best?
Right, because in the real world you don't know which model will handle your weird edge case.
Exactly, and another gap. Most multi-agent setups either split roles, planner, coder, tester, or they have everyone produce answers, and then an aggregator fuses them. Those approaches coordinate, but they don't actually teach agents anything new during the process. Lesson L, that's the framework here, pronounced Lesson L, focuses on the teaching part.
So how does the teaching work, step by step?
Picture three agents starting from the same piece of code. Each proposes a change, runs tests and a timer, and writes a short lesson about what helped or hurt. Those lessons go into a lesson bank. Before the next round, the system picks a handful of the most promising notes. Two signals drive that pick: notes tied to big speed-ups and notes that are semantically relevant to the current code. Then every agent incorporates those notes, tries again, and drops fresh lessons back into the bank.
And if a note sounds good but doesn't generalize?
They downweight it. The framework tracks how often a lesson actually helps across agents and rounds. If the note keeps paying off, it gets more influence next time. If it fizzles, it fades. It's like a study group where the tips that repeatedly help the whole class rise to the top.
Nice analogy. What did they test this on?
Two families of tasks. First, code optimization, taking correct code and making it faster, using ParEval and Polybench. Then standard code generation with HumanEval and MBPP, plus their tougher plus variants. For baselines, they compared against single-agent prompting, reflection loops like Reflection, role-based systems like MapCoder, aggregator methods like MOA, and strong proprietary models like GPT-4 and OpenAI's O3.
And the agents in Lesson L are big closed models too?
No, that's the neat part. The agents are small, mostly open models. Think QuenCoder and DeepSeek Coder style models. The point is to see if collaboration plus lessons can pull them up toward the big guys.
Okay, results time. Did the sticky notes actually move the needle?
They did. On optimization, the lesson-sharing team routinely beat GPT-4 and landed near O3. On parallel code in particular, it really shined. Average speedups around the 3.5 times range, and in one of the parallel suites, it even nudged ahead of O3. On code generation, it took the top spot on 3 of the 4 benchmarks, with MOA barely edging it out on the remaining one.
That's impressive for a bunch of smaller agents. Any sense of why parallel code shows bigger gains?
Parallel code offers more obvious, reusable strategies, like which loop to parallelize or how to chunk work, that make for crisp lessons. Those nuggets generalize well from one agent's success to the others.
What about cost and latency? Multi-agent systems can get pricey or slow if you're not careful.
The authors did a cost analysis and plotted speedup versus budget. Lesson L sat on the Pareto frontier, meaning strong speedups without blowing the budget. One run on the main optimization benchmark was in the same ballpark as GPT-4 and notably below O3. The trick is that lessons are short, so you make more calls, but each call is small. The trade-off is a slightly longer wait for the first useful answer because you need a few rounds of back and forth.
Makes sense. Were there ablations? I'm curious whether the gains come from the bank itself or from how they pick lessons.
They ran ablations and found two things mattered most. First, prioritizing lessons tied to speedups, not just any note. Second, that reweighting I mentioned, boosting lessons that repeatedly help across agents. Take either away and performance dips. They also tried adding more agents and more rounds. 3 agents get you most of the benefit. Adding more helps a little but with diminishing returns.
Let's sanity check the setup. Any quirks in the benchmarks?
A couple. They adapted Paraval, which was originally designed for code generation, into an optimization setting and fixed some benchmark issues. That's reasonable, but any adaptation can influence outcomes, so independent replication would be valuable. They also evaluate code generation with synthetic tests during the loop to avoid overfitting to the official tests, then grade final answers on the standard suites. That choice reduces overfitting risk, but brings in the possibility that some generated tests are imperfect.
So, not a red flag, but something to keep in mind when interpreting the numbers.
Exactly. Another caveat they note, everything here is function level, not full repositories. We don't yet know how lesson sharing behaves on multi-file projects, complex build systems, or long-running CI pipelines.
If I'm a team lead, how do I translate this to practice? What's the mental model?
Treat Lesson L like pairing a few strong junior developers who constantly exchange short postmortems. Instead of shipping raw code back and forth, they trade just the distilled what worked, what didn't, and why, and they iterate. You could imagine plugging this into a code assistant that behind the scenes runs a handful of small agent attempts, swaps lessons, and returns the best patch plus the rationale notes.
And I like that it's interpretable. Those lessons are readable, right? Not just mystery tokens?
Right. The notes look like micro-explanations a human might write. Reorder loops to improve locality. Avoid parallelizing the inner loop. Pre-compute prefix sums. That interpretability is a bonus for trust in learning.
What about comparisons to other multi-agent frameworks? Why not just have a planner, a coder, and a reviewer?
Role pipelines coordinate well, but assume you know the right roles ahead of time. The authors argue that on novel problems, you might not. Lesson L skips the roles and lets complementary strengths emerge as agents trade lessons. Aggregator methods fuse answers, but don't make the agents themselves smarter across rounds. Here, the agents improve as they learn from each other.
Any gotchas around fairness of the baselines?
They try to be careful, but there are unavoidable apples to oranges aspects. For example, Moe uses GPT-4o as an aggregator, while Lesson L keeps the agents small and open. And the cost analysis makes reasonable but still approximate assumptions about closed model pricing and sizes. So the broad story is solid, but exact dollar figures should be read as estimates.
All right, future work. If you were continuing this line, where would you go next?
3 directions. First, evaluate at repository scale, bug fixing across files, long horizon refactors, and integration with build systems. Second, turn the lesson bank into a persistent library across projects, with quality control so low-quality tips don't accumulate. Third, learn the lesson selection policy itself. Use bandits or credit assignment to pick the next few notes automatically rather than relying on heuristics.
Plus the usual robustness checks, different compilers, hardware, and making sure speedups don't vanish when you change environments.
Exactly, and stronger reproducibility kits never hurt. Containers, seeds, and public harnesses so other labs can rerun everything.
So, big picture, what's the takeaway for listeners?
Multi-agent coding isn't just about more voices in the room. It's about sharing the right kind of knowledge. If agents exchange concise, graded lessons, small open models can punch above their weight, often rivaling larger single models, especially on optimization and parallel code.
I like it. Simple idea, careful engineering, and results that move the needle without needing another giant model. That's a good day in research.
Couldn't agree more. That was Lessons Learned from NeurIPS 2025. Thanks for listening.
And if you try a lesson-sharing loop in your own tooling, let us know how it goes. See you next time on AI Podcast.